Today we'll analyze and design a multi-story building. It's a frame building, RCC frame building. It's a G+5 story building. So we will do the complete analysis and design of this building. So firstly, let us try to understand the framing of the building, how the plan of the building looks. So it is basically a five-story building which looks something like this. This is how our building looks like. So these are all beams. Okay, these are all beams. These portions, these are all beams, and these are the slabs. So it's a normal rectangular uniform building, and we'll put some columns also to understand it better. The columns will be like this, and this. It's a frame structure. We are not using any structural RC structural wall. We are just using beam and column. Simple slab, beam, column, and foundation element. Okay, so the first step would be to know the purpose, to decide the purpose of the building, for which purpose we are designing. Here the purpose is residential. For residential purpose, we are designing this building. Okay. Secondly, we have to start the process. So firstly, we can design the slabs. Okay. So for designing, I would say you follow the steps. That would be first you design the slab, then beam, then the columns, then foundation. This is how you will design the building. Why I am telling you design the slab first? Because it can be designed as per the method given in IS code. In IS 456 2000, in Annex E, I think Annex E it is given. Then how to design a two-way slab or one-way slab, continuous slab. Some coefficients, bending moment coefficients are given. Through that, you can design this slab. Okay, so it's simple. It's not that difficult. So you need to just categorize the slabs depending upon the shorter span and longer span. So one thing I forgot to mention here is span dimensions. So this is 3 meter, this is 4 meter, this is 5 meter, and this is 6 meter. Here this is 6, this is 4, and this is 5. So this is our span. So if we find out the shorter span, longer span to shorter span ratio of all the slabs, then you will find that this is 6, this is 3. So 6 by 3 is 2. So if longer span to shorter span ratio is greater than equal to 2, then it will be called as a one-way slab. That means it will behave as one-way slab. One-way slab is means the load distribution, the majority of the load will be distributed in the shorter direction. That is the meaning of one-way slab. Or and one more thing I can say that the bending, major bending will take place in the shorter direction. That means this is how this slab will bend majorly. It will bend in this direction also, but that will be not much as compared to this shorter direction bend. And the load that will travel along the shorter direction that will be maximum. There is also some derivation for that. If you do the derivation, you will be able to understand how the load is transferred in which direction depending upon this Ly by Lx ratio. So that is one thing. So first we'll categorize the slabs, whether it is a two-way slab or one-way slab. So you have now understood how to calculate Ly by Lx ratio and define whether it is a one-way or two-way slab. So this slab is a one-way slab, and the maximum load will, travel or distribute in the shorter direction. The shorter direction beams, the load will distribute like this. Okay, like this. In these two long beams, in these two beams, the major load will be transferred. This beam and this beam. Okay, in these two beams, load will not be transferred from the slab. This is as per yield line theory. I'm again telling this is little conservative method of analysis. This is as per yield line theory. But nowadays, much more advanced theory is there that is called your finite element method. Finite element method that is in use widely because nowadays mostly the softwares, design softwares are being used for analysis and design. One such software is ETABS. It is a widely used software all over the world right now for design of RCC building structures. So this is basically a FEM software. This uses FEM and some stiffness matrices to solve the problems. So I will come to these things later on. You just now understand there are two methods. One is this method yield line theory. One is the finite element method. So in yield line theory, as this is a one slab, so load will be distributed in this direction only. And all other slabs, if you calculate the longer to shorter span ratio, you will find that all other slabs are two-way slabs. So load will be distributed like this in both direction. Load will be distributed in both direction. Okay, load will be distributed like this, like this. So you do this thing to understand load distribution diagrams. This is how the load will distribute. This drawing is not in scale, so try to understand by the dimensions. This is how the load will distribute. Okay, so this is the first step to identify all the slabs. So this only one slab is one-way slab, and rest all other slabs are two-way slab. Okay, so as per IS code, IS 456-2000, you can do the all the slab design depending upon the Ly by Lx ratio. You will got the you can easily find out the moment coefficient values for midspan as well as the negative moment at continuous edge that I've already discussed. And there are nine edge conditions. Suppose for this slab, okay, for this slab, this is the longer edge, this is the shorter edge. So for this slab, the condition is one short edge is discontinuous. See, one short edge is discontinuous and rest all other edges are continuous. So the situation for the condition for this slab is one short edge discontinuous. You will get this condition in that table given in IS 456. So based on that condition, you will select this slab. This slab falls under that condition, one short edge discontinuous. So you will take the bending moment coefficient of that condition and apply to for the design of this slab. Okay, this is how you will design the slabs. Once you have designed the slabs, now you know the thickness of the slab that you have assumed at the time of design. Suppose let's say for this building, we are assuming uniform thickness for all these slabs. Suppose the thickness assumed is 150 mm. So now You know the slab thickness, so you can calculate the dead load on the slab. You also know it's a residential building, so you can calculate the live load and also the floor finish, whether you what kind of floor finishing you are going to do, whether it's marble or something else. That you can calculate, or it is given standard. Some standard is given in ISO 875 Part 1, dead loads, Part 2 for live loads. So here in this building, let's say we are considering the live load as 2.5, and this is in kilonewton per meter square. And let's say floor finish is, let's say 1.5 kilonewton per meter square. And you have to calculate the dead load of the slab, that is the self weight of the slab. How will I calculate? I need the self weight, I need the dead load in the unit of kilonewton per meter square. Okay. And now I know the unit weight of RCC, that is 25 kilonewton per meter cube. And I want per meter square load. So suppose this is your slab. Okay. And I want load per unit area. I want load per unit area means I want load in this area, in terms of this area. So what I will do, I have to multiply this gamma with this thickness. Suppose this thickness here I have assumed 150. So if I multiply here this gamma, this 25 kilonewton per meter cube with this 0.15, so what will happen? This is kilonewton per meter cube multiplied by thickness, that is meter. So meter gets cancelled. It becomes kilonewton per meter square. And I have multiplied this. So the left, which one is left? Left is this area. This area is not utilized in the multiplication. So it is coming out to be 3.75 kilonewton per meter square. This is the dead load that is coming on this slab. So now I know the dead load, live load, full finish. I can calculate the total load on the slab. The total load on the slab will be, if you add this, you will get 7.75 kilonewton per meter square. This is the total load on the slab. Now you know the total load on the slab. Once you design all the slabs, you are done with the slab design. You know the load on the slab. Now you have to design the beams and the columns, the frame. Now for analyzing the frame, for designing the frame, you need to analyze the frame. You need to find out the bending moment and shear force values in beams and columns. So for that, we will we will make 2D frames from the building. We will create some 2D framing system to analyze those, analyze the structure. So basically, what we will do, let's say we start with this. We start with this frame. Let's say we take out this frame, and as a 2D frame, we will analyze this frame. And similarly, we will analyze all the frames. Like this is one frame, and this is the second, this is the third frame, this is the fourth in the longer direction. And in the shorter direction, this is one frame, this is one frame, this is one frame, this one, and this one. So there are total 9 frames. So we have to analyze all the 9 frames individually as a 2D analysis to find out the bending moment and shear force. So let us first take one long frame that is on the exterior part. Let's see how to analyze. And one thing that is, I would say, we are analyzing here for gravity loads. That is for vertical loads we are analyzing. And for vertical loads, which method we will use to analyze? We will use the substitute frame method. Substitute frame method as explained in IAS 456. The exact clause number I am not remembering right now, but I will share with you. But this is mentioned in IAS 456 that we can use this method, substitute frame method, to analyze for the vertical loads. the frame analysis for the vertical loads. Now let me draw the frame, how it will look like one frame for analysis. So let me take one short frame for easier explanation. So I'm taking one short frame. Let me do it in the next page. I'm taking one short frame. So this is it's a G+5. So this is your ground level. The first, second, third, fourth, ground, first, second, third, fourth. So it is not matched actually. Let me do it in first, second, third, here ground, first, second, third, fourth. This is the two. Okay. And there are two more columns. One, two, three, four columns in the shorter direction. So let me construct that. First one is at a distance of 5 meters. Second one is at a distance of 4 meters. So this will continue actually. So this is how your 2D portal frame will look like. Now we need to calculate the loads on it to analyze the frame first. So basically when we will calculate the loads will be same as we are considering the plan of the building is same from ground to top. There is no deviation. So load on first, second, third, fourth floor will be same, exactly same. Whatever loads will come in the first floor beams, columns, it will be same for second, third, fourth, not the columns, only the beams. First, second, third, fourth. It will be same for all the frames. You just have to calculate on any one of the floor the load coming on the beam. That will be same for all the four level beams. Next, we will calculate for roof and ground. This will be different. For ground floor, the loads will be different. For roof, the loads will be different. For and rest this floor, the loads will be different. So for in these three locations, we have to calculate the loads. So how will I calculate the load? How we are going to calculate the load from slab to beam? So if you see carefully in beam in the beam, you need to calculate the UDL, and in the beam, how much UDL will act? One load that is coming from slab load that is transferred from slab to beam, that will contribute to the UDL in the beam. Plus second is self weight of beam. Uh, Self weight of beam, and third one is wall load. I'll explain the diagram. You will understand it. Be careful. See what happens. Suppose this is one particular slab. Okay, and this is supported by beams. This is our beam. Okay, this is the beam, and this one is the slab. So, how the loads will come on the beam? We need to analyze the frame. So, we need to put some UDL on this to analyze. In the roof, there will be some UDL on the beams. In this level, there will be some UDL. In ground level, there will be some UDL. UDL will be actually in all the levels, but we'll calculate these three portions only. Because these are the three different UDLs that we need to calculate on the beam, apply on the beam, and then analyze the beam, analyze the frame as a substitute frame. So, firstly, if it is a two-way slab and it's a kind of rectangular slab in the load distribution, suppose this is the shorter span and this is the longer span. So, the load distribution will be something like this. Will be something like this. So, what will happen in the shorter span beams? The load will be distributed like this. That means this much portion of the slab load will transfer to this beam, and this much portion of slab load will transfer to this beam. Similarly, this much portion of slab load will transfer to this beam, and again this much portion of slab load will transfer to this beam. So how we are going to calculate the load that is coming on the beam from this portion? How much load will come on this beam? So as we know previously, the loading intensity, that is 7.75 kilonewton per meter square. So we know the loading intensity. We know on how much area this load is acting. On this area, this load is acting. So we will what we will do? Loading intensity per meter square into multiply with this area. This area, let's say 5 meter square. We'll multiply with 5. Then we'll get some value. Let's say 38. So 38 kilonewton we will get, right? This is 5 meter square is the area. Area is 5 meter square. So if we multiply 7.75 kilonewton per meter square with 5 meter square, we'll get the total load from this portion of slab coming to the beam. That is 38 kilonewton. Now we need UDL for analysis. So total load on the beam divided by the length of beam. Let's say it is 3. So let's say it is coming out to be 13. Let's say it will not be 13, it will be less than 13, 12 point something. So let's say it is 13 kilonewton per meter. This is how we calculate the UDL on the beam. Similarly, you have to do this thing for all the slabs to distribute loads on all the beams. This is how we will transfer the load from the slab to the beam. And this is the first part. Second part is self weight of beam. How will you calculate the self weight of beam? Let's say, let's assume it's the cross section of the beam. We have to assume the cross section to calculate the self weight. Let's say it is 250 by 500. Now I need kilonewton per meter length, the load, and the beam is something like this. We know B, we know D. We don't need to know the length, as we already know, but we don't need it in calculation. To calculate the self weight of beam, what we will do, you again multiply the unit weight of RCC into B into D. This is what kilonewton per meter cube multiplied with B into D. That is, this will create meter square. This will be kilonewton per meter cube. This will again give me kilonewton per meter as UDL. And here I am utilizing this width and depth. I am not utilizing the length in the multiplication. So I will get this UDL per meter length of the beam. So this is how the self weight of the beam is calculated. And the third is wall load. If there is any wall, suppose there is a, this is the exterior portion of the beam. If there is any wall, so in this wall, you need to calculate the beam load coming from the wall, and the wall load will be something like similarly as like the beam we have calculated. It will be exactly same. Unit weight of brick multiplied by thickness into height. We need per meter length of the wall, the load. So we will multiply with height and thickness of the wall. Height and thickness. We will not utilize the length. Okay. The same way we will get the UDL coming from the brick wall. So these three components will be there. Now you have to see the plan where these walls are, where this slab loading is coming, where the self-header beam is to be added. By looking at this plan, when you will be calculating, you have to calculate each and every load at each and every beam. It will not be same for all the beams. So in some beams there will be, yes, a load coming from slab will be there in all the beams. Self-head of the beams will be there in all the beams, but wall load will not be there in all beams. Suppose the walls are placed at the exterior walls, exterior portion there are walls, but let's say interior portion there is wall, but there is no wall. Suppose there is wall, there is wall, there is no wall. So when you're calculating, you have to see the architectural drawing where the walls are placed, where the walls are not placed. If the wall is placed on the beam, then calculate the wall load and apply it on the beam. If the wall is not placed, then don't calculate the wall load and do not apply. And if the wall is placed and if the wall contains some opening like doors and windows, then you have to deduct that portion, because if you do not deduct, it will be designed for much more heavier load. It will be uneconomical design. Okay, unnecessarily you will be taking much more load. So you have to deduct that load. So reduce that. One method is do it exact analysis. How much area is left out or how much area is opened, to deduct that area, the load coming from that area, you have to deduct. Or one second one that you can do that is mentioned in ICE code. You deduct 20%. You just reduce the 20% load. Whatever load you have get, suppose you have there is a wall, but in this wall there is opening, and you have calculated the load, and it is coming around 20 kilonewton per meter cube. Now there is opening, so you have to reduce the load. Obviously, it will be less than 20 kilonewton per meter cube. One method is calculate the exact way. One is calculate reduce the 20% load. So how will you reduce? 20% load reduction means multiply with 0.8. 20% load reduction will be done. It will be 16 kilonewton per meter cube. Okay. So this is basically what 20. We have to deduct 20% from this 20. So 20% of 20 is how much? 20% of 20 kilonewton per meter cube we have to deduct. This is how much? This is 5. This is 4. This is 16. Same thing I have done directly. Okay. So this is how you need to calculate the wall loads. Now you will be able to calculate all the UDL on each and every beam from this formula. Slab load plus self-header beam plus wall load. In this way, you calculate the loads on all the beams, create this kind of frames, 2D frames, short frames, long frames, calculate the UDLs on roof, any particular floor level, ground floor level. And then finally, after creating all the loads and all, we will start analyzing by substitute frame method using moment distribution concept. So this I will not be telling you right now because this video has already been very lengthy. So let's stop it over here and we'll continue in the next class.